Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to actually talk about how we go about taking the limits of functions with more than one input. And it's a little bit trickier, definitely in higher dimensions, but I just want to start off and do another problem like we kind of did last class. So just sort of analyzing this function right here, which shows up down here. It's this weird kind of black hole looking thing. But I mean, really what it actually is it's sort of like a root function that's been spun around in the z-axis. But I want to kind of go through just how we would say the domain space, the range space, and then also do like just talk about a few level curves for it. So for domain, this is a cube root. Right, so there's no, issues here. Basically, every x value, every x value and y value is fine. And so the domain is literally just like all of R2. Just shade R2 or something, or just say R2. The range, though, is not quite that straightforward. So because of the fact that you've got these square terms in here, right, it would be impossible to plug anything in and get negatives, assuming, again, real valued function here. So the lowest this thing could ever be would be 0, right, if you plug in 0. But then it would go up to infinity. And that's, those are the z values. So you can also just say like z greater than or equal to 0. And that should be, you can kind of see that reflected here, like the red and green axis are the x and y, and we're plotting everywhere above that. This would go on forever and ever and ever. And it never gets below the xy plane either, because it just, sits basically, that point right there is on the xy plane. So for level curves, you just need to let like f of xy equal some constants and see what you get. So you could let, f of xy equal like 1. That's a pretty easy one. And then you could cube both sides, and you get just a, circle of radius 1, right? You could do, what's another nice one? Let like f of xy equal 2, right? So set that equal to the cube root of x squared plus y squared. In this case, then, when you cube both sides, you're going to get 8 equals x squared plus y squared. But you can see that as you go out, this thing has radius square root of 8, which I'm just going to say it's that. These look like ellipses too, but oh well. But that's square root of 8. We're going to say that there. But basically, it's just, what I just did is I kind of did, some circle around there, radius 1, and then radius 8 is somewhere bigger. And you just do, different level curves would just look like different circles like that. All right. So the main thing for today is to talk about limits of functions of higher inputs. So this thing is a 4-dimensional object, okay? What I actually have over here is like a level surface of it. So if I let, this is basically like f of x, y, z equals x squared y minus 3z over 2x plus 5y minus z. So if you got 3 inputs, right, you're going to plot in the 4th dimension, like the 4th spatial dimension. And so this is actually what Math 3D gives me if I plug in 1 here. So it's a level surface, just like we did in the last slide. And it's got a whole bunch of weird things going on. It's actually a very interesting graph to move around. And if you've have the time, you should check it out. You should like plug in like 1, 2 different things, constants here, and just see like the weird graph that you get. But limits sometimes are as easy as this one. This one's actually, though it's in 4 dimensions and all that, a lot of what you learn from BC Calc still applies here. So sometimes, if you want to approach the point 4, 1, -3, like x is 4, y is 1, z is -3, you can always, and it's a good thing to just do it right off the bat, just try and plug in that point, because maybe the graph is defined at that spot, and then it would, the limit would just be the function value, right? If it comes in from that side, both in all directions, basically. So you can always try this. So if we plug that limit in, we get 4 squared times 1 minus 3 times -3 over 2 times 4 plus 5 times 1 minus -3. And that is 25 over 16. And that actually is the limit. All we are doing is saying, it's like when you do a problem, something like, what is the limit of as x goes to 0 for x squared, right? And we know that's just 0, because it's just defined there, and you just plug in 0 and you get the answer. Now, if the bottom, when you plug it in, you get something like 0 there, that's when we're going to have to learn some other tricks. So it can be more complicated than just simply plugging in, but sometimes you can just plug it in and it'll work. All right, so the reason it can get harder is because we have a lot more stuff to think about. In 2D, okay, we look at this picture and this picture. If you plugged in 4 here, right, you would just get, I think I wanted this to be, let's just say this is 1 and this is 2. If you plug in 4 to this function, this piecewise function, you're just going to get 2. And so if you took the limit, it's not okay to just say you plug in 4 and get 2, right? We know that what a limit is like what is the value of the function approaching as you get close in both directions. And when you come in on this problem from the left and the right, you get 2 different values, right? The notation we use in Calc 1 is just like, let's say, so we're approaching 4, and we're going to say from the left, so we put the minus up there, right? And, for this, let's just call it f of x. It equals 1 from the left, but then the limit as x approaches 4 from the right of f of x is 2, and 1 is not 2. So this limit does not exist. That's what we do in BC Calc, and really that idea is still going to apply. You might have a problem like this in BC, and this limit exists as you approach 4. As you get really, really close, right, they both, whether you come in from the left or come in from the right, you still approach this value of 2. So in this one, the limit in both directions, which we then just write as 4, of like, say, f of x equals 2, right? And in 3D, it's the same thing, but the annoying part is that you have so many more directions to consider. Here, you're only going to have to consider coming in on the number line from the left and coming in from the right. But, so there's 2 directions here, okay? When we scale it up into just 3D, all of a sudden we have literally an infinite amount of directions to consider, which is really, really hard. So you could say, for this surface right here, the origin is like, if you trace it back, it's like this thing is supposed to be centered at the origin. And this like mountain flower petal thing, no matter which way you approach this peak, as you come in on the surface, whether you come in like, straight up that way, or you come in the side, or you come in this way, or this way, or this way, no matter which direction you approach the origin, right, you always are nearing this like peak right here, which I think is like about 5 in Z. So that limit, this one is good. This one is not good. Because if you approach the origin, so it's hard to read, but this is 0 and this is 0, you can see that as you come in from this direction, right, you're kind of getting a lower value than if you approach it from this direction. But there's literally an infinite amount of directions you need to check. So just because you find 2 that work doesn't mean that's going to be enough. You might need to come in from like a diagonal and check that. It can be really hard in 3D to find, whether or not it has a limit. And I'm going to show you tricks like that can kind of help you do it. But honestly, sometimes we just literally graph a thing and we can kind of look at this one and be like, and see that it's approaching 2 different values from when we approach the origin, so it would not exist in that one. So this just kind of sums up what I was just saying, but doing it more formally. So we have, I'll just kind of walk you through what this is saying. So it's saying if a function of x and y approaches some number L1 as xy approaches AB along a path, and that same function approaches L2, so some different number, as we get close to that point along a different path, and these guys are not the same, then this limit does not exist, right? It's just the idea I was saying of you could come into the origin kind of along that axis, and then you come in like perpendicular along this, and one time you're getting a value that's down here, and another time you're getting a value that's up here. And so those two are not matching up. It's really just the analog to this, but definitely harder to visualize. So sometimes I'm going to ask you to just do simply that. I'm going to ask you to show that a limit does not exist. And it's fine. You basically just get one counterexample. So you just need to show that as you come in from 2 different directions, you get 2 different numbers. Okay? And so in this one, if we come in on the different axes, like the x-axis and the y-axis, you're going to get the 2 different values. So let's just say we got x-axis here. So as we come in from the x-axis, then the xy point would approach basically... Well, no, so what I want to say is as the xy point now would just become an 0 point, right? Because we're on the x-axis, so the y is 0. And this then reduces this function to x squared and then minus, I guess I'll write it, 0, and then x squared plus 0. And then we know that with limits, right, we can reduce this. And so really, this is like the limit as x, I'm just going to write the answer because I think we know that that's a 1. But it's basically approaching 1, right? And then on the y-axis, we would change the problem to say, instead of xy, we would do 0y, and that approaches 0, 0, right? And then now the x's go to 0, and we get negative y squared and then over y squared. And then these cancel, and you get negative 1 this time. And that actually is what this picture is trying to show you. Maybe I'll erase this stuff. So yeah, as you come in, this is the y-axis right here. And so we'll do some colors here. So this right here is the y-axis, and that's the negative 1 value in there. And then this right here is the x-axis, And as you approach along that line, or that path, you're getting a value of 1. And since 1 and -1 are not the same, then we could say that the limit doesn't exist. And that's really just like this. It's just saying, like, as you approach from the left and right, the limit doesn't exist. Now, left and right is kind of arbitrary and hard. You just need to pick 2 different paths. That's the idea. So another trick you learn about in BC Calc is this squeeze theorem. And there's a squeeze theorem for multivariable calculus as well. But I want to make sure I review the idea for 2D first. So the idea is, like, if you can find 2 functions that bound another function, like for all time, then instead of working with this blue function, you could look at the yellow and like pink functions instead. So to put that like more formally, let's just say we have like there's no letters up here. So this is f and g. So this picture, it's like f of x is less than or equal to u of x. I think that's a u there, which is less than or equal to g of x. And I'm saying that if you can find these boundary functions like f and g, and the limit as you like approach whatever point you're concerned with, right? Like we'll call it a, of f of x equals the limit as x approaches a of g of x, okay? If these equal the same thing, then you have to have that the limit as x approaches a for the bounded function also is L. Basically, it's just squeeze. Sometimes they call this the sandwich theorem too. But like in this picture, we might be concerned with like what's happening right here. And we know that for both the magenta and the yellow, it squeezes the graph to kind of have a y value of 1. And so if those limits approach 1 at the origin, then the blue one has to approach 1 at the origin because it's always between the 2 functions. So that's the idea. And we can do this with functions of 2 or more variables too. And so I have some like tips down here. So I'll kind of go through these, I guess, too. So if you ever see like sine of something or cosine of something, those are always between 1 and -1. So those are kind of the classic examples of things for squeeze theorem. And so that's going to be used here. You also know that the absolute value of y is equal to the square root of y squared. And that is less than or equal to y squared plus something else positive, like x squared, right? This has to be bigger. And so sometimes you get these things where you get like a fraction with a root, and you'll see some of these. We're going to spend a few days with limits, and you'll see some of these too. But based on this, then you would have that like this thing must be between 1 and -1. So if you can sometimes craft a fraction with like certain roots and stuff, you can basically make a fraction sometimes that is between 1 or -1. And then this is just kind of a general rule for like a lot of limit algebra stuff, but always just try to get rid of the ugliest part of the function somehow. This doesn't always work, but like the idea is like you can usually manipulate with the easier parts, like here, the x to the 4th, but it's harder to get like some of these messy things into the problem. So sometimes if you can just like avoid them, it's a little bit easier. Okay, so I'm going to use this first hint kind of thing here though. So we have a sine function, okay? So we can say that sine function is bounded by -1 and 1. All right, and then x to the 4th is like a positive number, so it's not going to change any of my inequalities if I multiply both, like everything by it. So this is then equivalent to x to the fourth, or negative x to the fourth, is less than or equal to x to the fourth sine 1 over x squared plus the absolute value of y, and then less than or equal to x to the fourth. And now I have, my kind of three functions in a sense, right? Like f is like this guy, u is the one I want here, and g is this one. So I've like built up this boundary, right? And I know that just hit the arrow, as xy approaches 0, right? I know that I'm just thinking about how I want to write this. The limit, let's do that over. I know that the limit as xy approaches 0 for negative x to the fourth equals the limit as xy approaches 0 of x to the fourth equals 0, right? Basically, that's just like a direct substitution. You just plug in 0 for x. So both of those approach 0 as you approach the origin. So by the squeeze theorem, I'm going to just do an acronym by squeeze theorem, we know that the limit of, I'm going to do it in red because it's like my punchline here. We know that the limit as xy approaches 0 of this messy looking thing also has to be, has to be 0. There we go. And that's it. So we're going to do a few days with this kind of stuff because it can be kind of tricky. A lot of students always want to ask, is there a L'Hopital's rule for functions of higher inputs? And technically there is, and I'm going to show you something like it, but it's really messy and hard to work with. The thing goes back to just the idea that there's so many different directions to check. And when you're doing L'Hopital's with like a function like this thing or something, you basically are just checking two like tangent lines and looking at their ratios as you get close to a point. But here, down here or down here, there's literally infinite amount of paths to come in on. And so there's infinite amount of tangent lines to consider, and that's a really, really hard thing to do. So I will say something about it, but it isn't something that we can sadly use. So we have to kind of use some other tricks.